We will be discussing the rebound hammer test, a widely used method to determine the compressive strength of concrete in a non-destructive way. This test is essential for assessing the quality of concrete structures. The equipment used for this test is the rebound hammer, also known as the Schmidt hammer. We are using the concrete test hammer N L4021X/001N, which was built by NL Scientific. This hammer is lightweight, portable, and specifically designed for quick on-site assessments of concrete strength. The Schmidt rebound hammer works on the principle that the rebound of an elastic mass depends on the surface hardness of the material it strikes. Although there is no direct theoretical correlation between concrete strength and rebound number, empirical relationships have been established within specific limits. For instance, Colex research attempts to connect rebound numbers with hardness, measured by the Brunel method. It is used for estimating the compressive strength of concrete, identifying weak zones and structures, and ensuring overall construction quality. Let's take a closer look at the key components of the rebound hammer and their functions. First, we have the outer body. This is the durable casing that encases and protects all internal components of the device, ensuring safe operation. Next is the plunger, which comes into direct contact with the concrete surface during testing. It's the primary point of interaction between the tool and the material. Then we have the hammer mass. This component applies force to the plunger to generate the impact needed for the test. The mainspring is what generates the impact force. When compressed and released, it propels the hammer mass forward. The latching mechanism locks the hammer mass to the plunger rod, ensuring a controlled and precise release of force during testing. Finally, the sliding rider measures the rebound distance. This is recorded as a rebound number, which you can see on a scale ranging from 10 to 100. This number directly correlates to the concrete's strength. These components work together to make the rebound hammer an effective and reliable tool for evaluating concrete strength. Procedure of application. Before starting the test, let's prepare the instrument. First, select a rebound hammer that is suitable for the type of concrete you're testing. Ensure the hammer is functioning correctly by checking its readings on a steel reference anvil. Next, map out the test grid. A minimum of 12 readings is usually sufficient. If needed, prepare the surface. This may involve smoothing it with a grinding stone to ensure accurate results. Once the grid is set and the surface prepared, perform a few test impacts to verify that the rebound hammer is operating correctly. Now, let's determine the rebound hammer readings. Start by performing an impact at the intersection of the grid lines. This will be your first test point. Move to the next point on the grid and perform another impact. Continue this process until you've taken enough readings. Once all necessary impacts have been made, terminate the series and review the results. Next is the uniformity assessment. Move to a new location on the structure and perform the rebound hammer test again. Repeat the process at several different locations until sufficient data has been collected, and that completes the process. While the Schmidt rebound hammer is a quick and inexpensive way to test concrete uniformity, there are important limitations to consider. First, the surface must be smooth for accurate testing. Rough surfaces should be smoothed using a carborundum stone. If the specimen is not part of a large mass, movement during impact can reduce the rebound number, so it should be rigidly supported. Rebound numbers are typically higher for 7-day-old concrete than for 28-day-old concrete of the same strength. Rebound testing should not be done on low-strength concrete, less than 7 megapascals. The moisture condition of the concrete affects the readings. Drier concrete gives lower numbers. Additionally, different aggregates and cement types, such as high alumina or supersulfated cement, can cause variations. Lastly, carbonation in older concrete may result in rebound numbers up to 50% higher than for uncarbonated surfaces, affecting accuracy. This is the record after tests conducted on 5 locations, and the data have been extracted from the graph. In conclusion, the average rebound number results are as follows. Location 1, 33.75. Location 2, 33.75. Location 3, 0.75. 32.33. Location 4, 32.67. And location 5, 33.75. These results indicate that the average rebound number for the tested concrete surfaces falls within the range of 30 to 40. This reflects a good quality concrete surface layer. The next test we will be exploring is crack depth testing using the ultrasonic pulse velocity method. This method utilizes ultrasonic waves to determine the depth of cracks in concrete, ensuring the structural integrity of various structures. The type of equipment used are the ProSec Pundit 250 array, an advanced ultrasonic tester. It features high-frequency transducers, a digital display for crack depth and wave speed, and the ability to store test results for further analysis. The applications. This test is ideal for evaluating structural integrity in bridges, buildings, and other concrete structures. Procedure preparation. Clean the area around the crack. Apply coupling gel to enhance wave transmission. Wave propagation. A transducer generates a pulse of longitudinal vibrations, transmitting it into the concrete through the coupling gel. The pulse undergoes multiple reflections within the concrete, creating stress waves. The longitudinal waves are received by another transducer, converted into electrical signals, and measured using electronic timing circuits. Testing. Place the transmitter on one side of the crack and the receiver on the opposite side. Using the surface transducer position, record the data in order to collect the data of compound measurement, perpendicular crack depth using the equipment. Follow this step, select compound measurements, and then crack depth. Set the parameter B and measure the distance. Place the transducers in the first position and press Start to measure T1. Move the transducers to the second position and press Start to measure T2. The display will show T1, T2, calculated crack depth. Save the results or repeat the process as needed. The limitations for this test. This method is not suitable for cracks smaller than 1 millimeter. Uneven surfaces may affect accuracy. This is the result of the experiment for point 1 and 2. Based on the result, the crack depth is not severe. Last is the half-cell corrosion potential meter test, a non-destructive method used to assess the risk of corrosion in reinforced concrete structures. The type of equipment used were a half-cell corrosion potential meter, which includes a reference electrode, typically copper-copper sulfate, a high-impedance voltmeter to measure potential differences, connection wires, and a sponge and gel to ensure proper electrical contact. The applications of this test helps to identify active corrosion areas in concrete, assess corrosion risk in reinforced concrete structures like bridges and buildings. Procedure. Prepare the electrode's rod. Electrode. Before filling, remove the red cap with the wooden plug and soak it in water for about an hour to allow the wood to saturate and swell. Copper sulfate solution. Prepare a saturated solution by mixing 40 units by weight of copper sulfate with 100 units by weight of distilled water. To ensure the solution remains saturated, add an additional teaspoon of copper sulfate crystals into the electrode. Fill the electrode as completely as possible, minimizing air in the compartment, to ensure the solution contacts the wooden plug during measurement. Preparation. Clean the concrete surface to remove dirt and coatings. Ensure the rebar is accessible and properly connected to the reference electrode. Testing. Setup. Wet the surface using a sponge or wetting agent to improve conductivity. Place the reference electrode on the surface, and the voltmeter will measure the potential difference between the rebar and the reference electrode. Measurement. Move the electrode across a marked grid on the surface. Record the potential readings to create a map of corrosion risk across the structure. Interpreting results. Less than negative 200 millivolts, low corrosion risk. Minus 200 millivolts to minus 350 millivolts, intermediate corrosion risk. Greater than negative 350 millivolts, high corrosion risk. Limitations. Accurate results require proper surface preparation. Results can be influenced by moisture levels, concrete resistivity, and surface contaminants. Conclusion: the half-cell corrosion potential test is a vital tool for early corrosion detection, helping ensure the longevity of reinforced concrete structures. This is the result of the test conducted. Based on the data and the value table, the component tested have visible corrosion.